Everyone, let's get started. Please don't talk about the exam because some folks still have to take it. But they should be done by Friday. So I asked the TAs to try to grade over the weekend, and then we hope to get them back sometime next week. And what else? Homework 3 is due today, but you can have until Friday, I think. And programming assignment 2 is out. And yeah, so please sign up for your group by Friday. I think there was some confusion in the first one. So once you sign up for a group, please don't switch the group. Like the group on Canvas should line up with the group on Gradescope. It should be set by this Friday, so you have enough time to work on it. And please at least look at it soon, because it's more complicated than the first one. And is that it? Yeah, I changed the schedule of the homework, so the next actual written homework is coming out Monday. But we still have the schedule of every 2 weeks. It's just shifted forward a little bit because the lectures didn't exactly line up with the initial schedule I had. Yeah, questions? Any issues? Cool. Okay, so today we're going to do more MPI, but before we do that, I'm going to finish up the slides from last lecture, which were, if you remember, was about collectives like all to all and all gather and stuff like that. And the last thing that I wanted to talk about is there's a question last time about this actually, which is like how do you do many to many with different sizes of messages? So remember that we talked about all to all, which is like a collective communication where every processor has some data that they need to send to every other processor, and it's different that they want to send to every other processor, but it's the same size that we had initially that they want to ship. But however, how would you do it if everybody had different sizes of messages that they wanted to send with still good bounds? So yeah, we're going to do that first. That's a generalized version of all to all. And you can think of it like this matrix. If you remember, all to all is basically like matrix transpose. The way to read this is like the first one is the source and the second one is the dest. So this is like message 0 sending to message 0, message 0 sending to message 1, and so on. And this is, you might imagine that it's natural for these to have varying sizes. Like for example, the diagonal, like usually you don't need to send to yourself. So you could initially mostly set that to 0 anyway. Yeah, and you can bound this. You can bound a bunch of things by just doing the sum over the rows and the columns in the matrix. So if you sum over j, which is you fix the row and then you send over to j. That's the maximum amount that any processor has to send. And if you sum over I and fix j, then that's the maximum amount you need to receive. So if you sum along the column, that's how much message, or that's how much processor j needs to send. If you sum across the row, that's how much processor I needs to send. Does that make sense? Cool. So it kind of looks like this. This is just an example with p equal to 4, and suppose we're just looking at processor 2. So processor 2 needs to send this chunk of data to processor 0. It needs to send less to processor 1 and about the same amount to processor 3, and it's not sending anything to itself. Because usually in algorithms, it's already on your processor, so why would you need to send it? And the way you can even this out is that you cut up the even pieces, or you cut up all the pieces into 4, or into p, which is the number of processors that you have, and then you ship. So for example, like this part with 2, 0, basically the intuition is that you're not initially going to send all of the data destined for some process to that process initially. You're going to evenly spread it out across different processors, and those processors are going to help you send it to other places. This is kind of like how we do like broadcast or reduce. A little bit like reduce, all reduce kind of, which is like the processors share in the work to do the sending. So yeah, you cut up the pieces, like this all is going to processor 0, but we cut it into P0, P1, P2, P3, and we do the same for all of the other pieces. And then we take the pieces that are labeled P0 and we send them to P0. So notice that not all of them are going to end up on P0, but we're going to forward them along. And this becomes an all-to-all with now everybody has even size, which is S, the maximum size that anybody needed to send over P, which is the number of processors. And that's how you make the communication size uniform. And then the second part, so like I said, we're not done because not everybody has what they needed at the end. So now you have to route the evenly sized pieces to their correct destinations. And that is an all-to-all, another all-to-all with max message size R over P. And remember, R is the most that anybody has to reduce. And we have the runtime for all-to-all, which is tau times P plus mu times M times P, and M is the message size. And so the stage one, we had to send an all-to-all with message size S over P. Remember that we made it uniform, and you can just cancel out the P's. Then stage two, we do another all-to-all, but now with the message size is R over P. So if you add them up, the total time is tau times P, theta tau times P, times mu, and then in parentheses R plus S plus R. Okay, one thing that I glossed over is this doesn't immediately work because we can cut these up into even pieces, but if you just ship like this block, you concatenate them and then you ship the block of data, you don't know where it ends for every single process. So we need some kind of boundary. And that is easy. We could just put like a special character or something. So the message size becomes very slightly bigger plus P because you need one boundary for every process because you're cutting every piece destined for everybody into evenly sized pieces on P. Yeah, so you have constant space to mark the boundary of every data for every processor. So when you multiply this by P again, you get plus P squared, which is which still comes out to the same thing if P squared is much less than S plus R. Yeah, so just to recap again on these bounds, we had broadcast, reduce, all reduce, and scan, and those are tau log P plus mu M log P. This log P comes from this last tree-like reduction, and M is the message size. And then the more complicated ones are gather, all gather, scatter, which are tau log P plus mu MP. The difference between this is log P and this is M, this is log P and this is P. In gather and scatter, for example, like the data doesn't become smaller when you go up the tree, or sorry, not smaller, but it doesn't stay fixed when you go up the tree. Like, so for reduce, if you reduce two things, you get one thing. And if you reduce another 4 things, it becomes one thing, and so on like that. So in the end, you get one result per vector that you're trying to reduce. However, for gather, like the data is doubling when you go up the tree. So that's why it's P, because there's log P levels, but it's like M, 2M, 4M, and so on. Yeah. And this is just a recap for the bounds for all-to-all, which are different for arbitrary and hypercubic. Remember, like for arbitrary, you can do the cyclic shifting, and for hypercubic, you need to do something more complicated. Questions? Oh. Okay, so that is it for high-level collectives, and then we're going to move on to how do you do this in MPI. So we're just going to recap very briefly about what we talked about last time regarding MPI, because you're going to need this to implement the primitives. First one is synchronization, which is implemented with MPI barrier, and you put in the communicator. And remember, in MPI, the communicator is kind of like describing the set of processors that you have. So in the beginning of time, you have one communicator, which is all the ranks. And we will talk about later how, like if you need a subset of the ranks, how you would do that. But for now, communicator, in the beginning, you get one communicator, which is everyone. And synchronization is just saying it gives a stopping point in the code, and it's saying no process can go past the stopping point until everybody else has also reached this point. So regardless of, and they may go at different speeds, so regardless of how fast everyone is going, you have to wait here until everybody is finished. So yeah, and the way to tell whether you need this or not is if you can check if you need the results of it on other ranks or on your own rank even before you proceed. Yeah, and you can, so remember like the way that MPI works, you write the program and every process executes it, but there's no like, if one processor calls the barrier, everybody has to call it. You can't be like, if my rank is even, I'm going to call barrier, otherwise not, because that's advanced synchronization, but that's too advanced for synchronization, but you could like split the communicator later that we're going to say to like stop all the even processors. You can make a new communicator with all the even processors and then call barrier on that. Okay, so also to recap, we did MPI, we did send and receive last time. So send and receive, you pass in the avoid pointer for the data, an int for the count, which is how many you're going to send, a data type, which is how many, just the type of whatever is in here, a destination rank, a tag, and the communicator, which again is like the world. And this is blocking send, which means that it will not proceed past this point until the send has completed. And then on the other side, every send has to be paired with a receive. So receive looks very similar to send. Again, there's this void pointer, count, and data type source. So these are all the same as they were in send. The only difference is now you get an extra thing, which is status. And we'll talk about more about status later, but status is a way to check, like, basically if you have received the thing. And this again is blocking receive. You will not go past this unless unless you have actually finished receiving, unless the data is actually in this void star. And you can pass count more than the number of actual elements that you get, but you cannot pass count less. Yeah. Questions? Okay. So this is an example send and receive. Just suppose that we have two ranks. We make this vector, and we're going to send the entire vector. This is called tab. Well, first we set tab n-1, which is like the last element, to 13. We send all of it to the destination process, which is 1. And then on the other side, we receive, and we receive n. So we receive the entire vector, but then we print out the last one, and then we should print 13. That's the tag. So you can, the tag, for send and receive, if you want them to pair, the tag should match. But you can also pass in, there's like an MPI constant called like MPI any tag. And in that sense, and then the tag would, it could match anything for the receive. For convenience, you could always just have the tag to like 0 or something. Tag is like, if you're doing multiple send and receives from the same processor, to and from the same processor, then you may use the tag to differentiate the messages. Okay, so tag, yeah, you have to send a user-defined tag to help the receiver identify the message, and you can specify MPI any tag if you don't care about the ordering, or maybe you're just getting one, so you want to make it less complicated. The tag is just an int. Okay. Yeah, so like I said, every send has to be matched by corresponding receive. Otherwise, for the blocking case, the thing is not going to finish. And for matching, they have to match by the envelope, which is the metadata. So the entire communicator, the source rank, and the destination rank need to match. So yeah, like if you're sending from 0 to 1, there has to be a corresponding receive from 1 to 0. The tag and the type or the size actually do not have to match. The buffer that you allocate on the receive side just has to be at least as big as what you're sending. Yeah. And blocking, like I said, the entire thing, the program stops for send and receive until the thing is finished. Okay. So yeah, so we can do an example. This is similar to what we had before, except now we just have an int x rather than a vector. And like you were mentioning, this is the tag. And if they don't line up, like this is 111 and this is 222, then this thing will never finish because the send is waiting for a corresponding receive and the receive is waiting for a corresponding send, but they don't line up. Another example, suppose you have two sends. It's also, yeah, so if you have multiple sends and receives, you want to be careful about the ordering of them. So this is similar to what we had. This is just an example. We have a vector x, two vectors x and y, and they both have some size, which is 16. And we again have two ranks, and we set position 13 as 13 here, and position 13 as 0.13, but it doesn't really matter what's in them. And then we have two send and receives. We send vector x, 16 ints, to destination 1, then we send vector y with 16 elements to destination 1, and the tags are 111 and 222. So this is what I was saying, like the tags may be different if you have multiple send and receive between the same pair. And here, this is MPI float, because the y vector is float. And then here, the person messed up the order of send and receive, so they put the receive for y first before the receive for x. And this is wrong because rank 1 will be waiting for y, and rank 0 will have sent x and be waiting for the acknowledgement, but rank 1 cannot receive x until it has received y, but it's rank 0 is not going to send y until it has finished x. So yeah. So then you have deadlock again because neither can proceed. You could, is there a way to fix this? Yeah, you could fix this, but not by changing the tag. And we'll talk about how to fix it in a bit. Yeah, so in this simple case, you can just reorder x and y to fix it. But if you have more complicated cases, that may not immediately resolve it. Okay. Yeah, so like I said, you can use MPI any tag if you don't care about, yes. Yes, of course.
I thought you said that send doesn't have to wait for acknowledgement, like may wait for acknowledgement. So why does rank 0 processor block until 111 tag is on?
Send blocks, this version of send blocks until it has been received.
Oh,
yeah. There's many versions of this. Yes, really good question. There are many versions of send. This one is the most simple version and it will block, but we will shortly go to non-blocking versions. But in this one, in this example, you don't need the non-blocking version because there's no like actual cycle, or it's really just from 0 to 1. There's no cycle between 1 and 0, so you can just resolve it by flipping the order. Question. Yeah, so you can use, if you don't care about the tag, you can use MPI any tag. There's also a corresponding MPI any source. So if you don't know necessarily where your message is coming from, you can pass in any source to receive from any other processor. And you can use MPI status to check the received message. So this is status, and then you pass it in as the last parameter into receive. And this is just trying to receive one int. And then you can query source. So you pass in MPI any source and MPI any tag here. But if you want to get the actual source and tag that you got, then you query it stat.mpi source stat.mpi tag. Depending on the program, you may or may not actually care what the source and the tag are, but in case you need it. Okay. Yeah, so this is slightly more complicated. You go up to, so size is the number of communicators in, or the number of processors in the communicator. So size is like this, and you have the status, and this is a for loop over the size, which is the number of processors, and then you receive from any of them, or you receive from all of them, which is just one int, and you can output the source and the tag there as an example. And then otherwise, so this is all the other ranks, and all the other ranks are sending their own rank. So, or sorry, yeah, all the other ranks are sending their own rank. And then the tag, the destination is 0, and the tag is the total size of the world minus your own rank. So actually, yeah, so you would receive them all, but actually, I guess here you would also receive them in the order of ranks because you go from 1 up to n. Yeah. Yes, sorry. Oh, yeah, sorry, that's right. Yeah, you put the 4 is serial, but the receives. Sorry, yes, I was confused. The receives may finish in any order depending on when the actual data got there, which is dependent. Like it's not necessarily. By the way, sorry, that's my mistake. So yeah, that is a bit subtle actually. So even though this is serial for the receives, like by the time you get here, it may not be guaranteed in the rank order. Okay, and finally, I talked about like in some cases you may not just solve some issues by just reversing send and receive. And one situation is like if you have cyclic dependencies like this, your processors are zero is trying to send to one is trying to send to two, so on. P minus one is trying to send to zero, all the way like that. And that is like a common thing that we want to do. Like for example, we even do that if you want to implement all to all with arbitrary permutation. And one way to do that is like you send to the next one and then you receive from everybody's destination and source, so you can send like that, destination and source, but depending on, so everybody's trying to send this way and everybody's trying to receive in the reverse direction, but the send may not finish until, but everybody's trying to send first. Yes.
Could you also go over what you meant by multiple and arbitrary permutation?
Oh yeah, you're good. I'll try to explain it, and if we need to pull up the slides again, we can. As a reminder, all-to-all is every processor is trying to send some data to every. It's like the matrix transpose, and the easiest version is if everybody needs to send the same size, and the communication patterns that you can do that with are different depending on if you have a hypercubic permutation underneath or if you have arbitrary permutation. So if you have arbitrary permutation, you can basically do like cyclic shift. And if you remember from last time, the initial version is like everybody, you do a serial 4, and then you're like P0 sends to P1, and then P0 sends to P2, and so on like that. But then there's this issue, which is that if you don't offset them a little bit, then everybody's trying to send to the same processor. So you need to offset them. So like in the first round, P0 sends to P1, P1 sends to P2, and so on. And then moving on like that, like P0, in the next round, P0 would send to P2, P1 would send to P3, and so on like that. So you offset it based on your own rank. Good question. So that is actually what happens here because, yeah, because you need to send in a loop, basically. I guess not exactly because you don't need to send. Actually, kind of. Yeah. So you like if you think about the matrix in this version, you shift so everybody starts along their main diagonal, and then you kind of move like the diagonals further right, and each one of those is one cycle. Does that make sense to everyone? People remember that? Okay, cool. So you can implement it. One way that you might try to implement it is everybody sends to their next neighbor, which is just rank plus 1 mod by size, and then everybody tries to receive from their previous neighbor. You could put MPI any source. You could put your own, like this is rank minus 1 mod size as well. But this will not finish because everybody's trying to send, but nobody is receiving yet. So this is not going to proceed until they receive. And if you flip them, it's also not right because everybody's trying to receive, but nobody has sent yet. So it's just the reverse issue. And the way to solve that is, one way to solve it is using non-blocking communication. So rather than send, there's many variants of send and receive in MPI. There's iSend and iReceive, which are like the most, I guess maybe the second most common versions of send and receive. And that initiates the transfer, but it doesn't block until you succeed. So you can keep going. And it allows you to avoid the deadlock like we had in the previous slide. And it can also, when you actually try to write high performance programs, it hides the latency because you can overlap the communication with the computation. So you send, you call like iReceive, or you call iSend to send some data, and you don't need to wait in your actual program. Like if you have some local computation, like adding up numbers, for example, or computing a local matrix multiply or whatever it is, you can do that while the send is happening in the background. And similar for the receive, you don't have to, if you need the data, then you have to wait for the receive to finish. But if you can have some work that you don't need your receive to data for, you can also do that with iReceive. Yes.
Wait, so you can do like your work after you start the send. How do you know that your work actually?
Yes, you need the result of what you're going to send before you send it. But if you have other stuff that you could possibly be doing. Yeah. Thank you. Really good question. You cannot touch the buffer. Yeah, you cannot. Yeah, that's also another thing, which is like when you pass in the void pointer at the beginning of I send and I receive or send and receive, it is undefined if you touch that data like in void star buff until if unless like there's a status that you can query, and then if you query the status, that will tell you whether it's finished, and then you can touch the buffer. But until then, you cannot. Yes. You can neither read nor write it. But I will show you later, like, yeah, so you get this request. So the only difference between iSend and iReceive, the difference between iSend and send in terms of the API is now that there's an additional request thing here. And in the request thing here, you query, similar like how we were querying status, you query request to ask if it's finished or not. And then if you query request and then it's finished, then you can look at or write to this void star. Really good. Yeah. Yes. So yes, to be clear, if you're trying to send something, all the stuff that you're sending needs to be present here already. And you cannot reuse this data or reuse this memory until this is finished, which you can tell by asking for a request. So like you could allocate some other data and then do some other side computation. Cool. Yeah, and then the way you ask if it's finished, there's two ways. One is called MPI wait, and it takes in request and it takes in status. And MPI wait, it's kind of like, it's not really like synchronization in the sense that it's just for you, but it will just not pass this point until the request tells you that it's finished. So one thing that you could do is like, you do your iSend, and then you do a bunch of other stuff, and then you call wait at the bottom. And then you wouldn't proceed until you finished the entire send. And similar for the receive. And for the receive, that would be fine because, or yeah, receive is, you would probably use this when you use receive because after you call wait, then the data that you wanted is in the receive, so you could do your computation on what you got. And then there's also MPI test, which is it similar to wait, except it will not block. So it passes in a request, a flag, and then a status, and you get the result in flag. And it just tests whether it's complete, and it doesn't wait. So you could do this in a loop, or if you, yeah, like you could implement wait by putting this in a while loop.
Wait probably has some extra stuff to figure out the implementation details so that it doesn't put on a while loop.
Yeah. Yes, exactly. So you probably would not want to implement wait with just a while loop. You may like use back off or something. Like you wait, like maybe you give it like a few cycles between every iteration of the while loop, so you're not just spinning. So now we can fix this cyclic dependency with I send and I receive. So now before we had send and receive, and to use the non-blocking version, we have request, and then we put the I receive first. We're getting one integer, and we have any source, and the tag is 13. Doesn't matter what it is, it just needs to match. And then this kind of like spawns off, and we call the send, and then we wait. So you pass in the request, and you pass in the status, which is somewhere, I guess not shown. The status is something that you fill also with the request. So like let's go back for a second. Yeah, so here you pass in the status, and then wait will fill in status with some metadata, and then you can query it. You can query it. It's like a struct, you fill it in, and you can query it afterwards, but if you don't care and you just need to proceed, then you don't need to ask for it.
Like, why it's not actually filled in? Like, if you try to access why it's not actually filled in, or while the receive is still going, then it'll just explode.
Yes, or it probably won't explode. It will just, you'll get like garbage. Like X and Y, you have to declare them on the local side, and those are like buffers that you're trying to fill in. And you just cannot touch Y until you pass this wait. Or you can, but the result is not guaranteed.
There was like something I was doing one where I tried to touch some buffering or something, and it like it just died at like 6 or something. I don't know.
I see. It's better in some ways, I guess. Yeah. I think it's undefined. Probably depends on the implementation of MPI.
If it was a ISAM instead of a SAM, you could do it in like any order.
Could you do it in any order? You could. You would need to pass in a second request because the both functions take in request, and you would need to declare two because you can't share them. And then I guess you would serialize them in the wait because you would either have to request, like you would have to be like wait request and then wait request two, or vice versa. But you would serialize them in the wait, but you could spawn them arbitrarily in the send and receive. Questions? So that's point-to-point communication, and in PA2 you have to use those to implement the collectives that we will do now. Okay. So to recap about the primitives, there are several, but we're going to do two first. This one is broadcast. So in broadcast, some processor has some data, and then after the broadcast, every processor has that same data. So there's only one. This doesn't have to be a single, like scalar, int, or whatever. It could be a vector, but it just the same thing needs to show up on every processor at the end. And then there's gather and scatter, which are inverse of each other. Scatter is every process 0 or any process has some data, and it's different for the data that it needs to send to every other process is different. So like this is going to process 0, this is going to process 1, this is going to process 2, this is going to process 3. And then at the end, this is processes and this is data. So now process 0 has 0, process 1 has 1, process 2 has 2, process 3 has 3. And gather is just the reverse of that. So every process has some data that it needs to collect onto one processor. And again, the rank does not always have to be 0, but it's illustrated this way for simplicity. And we talked about last time some methods that you can use if you have arbitrary source. Like the easiest way is like you send to rank 0, and then you do the algorithm as if to rank 0, and then you just ship the result to wherever you're actually trying to go. So there are MPI functions for all of these collectives. Broadcast, you just send one message from the root to all other processes. So everybody who's participating in the broadcast has to call broadcast. It's not just the root that needs to, it's a bit confusing, but the way that I think of it is in MPI, like when you call the collectives, it's not that everybody is doing the broadcast, but it's everybody is participating in the broadcast. So broadcast, you pass in the pointer to the data that you're trying to broadcast, the count, the type, and the root, which is an important part, and the communicator. And so the meaning of this buffer is different depending on if you're the root or not. If you're the root, the buffer is the stuff that you're trying to send to everyone else. And if you're everyone else, the buffer is where you're receiving the data. And this is an example of how you would call it. So the rank, if your rank is 0, then you're trying to send x, which is negative 13.13. And everybody, there's no like if rank equals 0, then call broadcast. There's just broadcast, which is data, size, type, root, and world, which is just the entire communicator. And then at the end, everybody will print x, which is negative 13. For yeah, so for the here, like since the root is going to be 0, we set x equal to whatever we're trying to broadcast. But x is not set by anyone else. Like for every process is running this code. So every process is going to set x here equal to 0.0. And then if your rank is 0, you're going to set x to this negative 13 byte 13. And then we call broadcast here. So everyone, there's no, I was just saying like there's no, if your rank is 0, then you call broadcast. It's everybody will call broadcast, and the root is set here, and to 0 in this example, and then everyone is going to get 13.13 into their x.
Okay, I see. So we call broadcast on everything, but
Exactly. Yeah. The root is whatever's in the root is going to be sent out, and then and then that data is going to be put into the source buffer or receiving buffer, which is called x on every other. Yeah, this is why I'm saying it's a bit confusing. Like they're usually called the same thing, or depending on how you program it, like you could declare another y, and then, but then it wouldn't really work because if you're trying to send, like if you declared another x and y, and then you wanted y to be the receiving variable, then somehow you would pass in like x here for some process and y here for other processes. So usually the way it works is that like there's just one buffer, and depending on if you're the root or not, it is both. It is either the send or the receive buffer. Yep, does that make sense? Good question. Yes, please.
Broadcast answer. They assume that
It's a good question. It's a really good question. So as you can see, like in the actual, when you actually write MPI, you don't need to care whether it's hypercubic or not. In the homework, you will have to care whether it's hypercubic or not, but for many of the primitives, it doesn't matter. I think only for all to all are there different algorithms for hypercubic or not. Like for broadcast, the best you can do on any architecture is like this tree-like reduction, or sorry, reverse tree-like reduction, I guess. So yeah, the reason that we were talking about the algorithms last time is like there was this question, which is like, why would you care about the permutation or the algorithms if you can just call MPI broadcast? Because it's good to have a deeper understanding, and also because if you need to think about how to implement them or reason about the performance, you need to understand the algorithm. Oh yeah, so hypercubic is like you have like binary numbers up to like all zeros up to all ones, I guess. And then hypercubic is just every rank is denoted by this binary string, and every rank is connected to only the ranks that differ in one bit position. So like 0, 0, 0 would be connected to like 0, 0, 1, 0, 1, 0, and then 1, 1, 1. Or sorry, not 1, 1, 1, 1, 0, 0, like that. Yeah.
What's the alternatives to hypercubic that are actually used in practice?
There are so many. We will do topologies later. Like there's as many topologies as like people out there. Yeah, hypercube is a good one because hypercube is like they spend a lot of time studying this in like the 70s because it's simple and it has really nice properties. For example, the number of links is relatively small. Because if you remember, we were talking like when we first started talking about permutations, the most ideal is if everybody was connected to everyone else by one hop. But that is unrealistic because then you'd need n squared links, which is too many in practice. So hypercubic is nice because, as we saw through the algorithms, a lot of algorithms can follow this kind of communication pattern where you only need to send to one of these neighbors at a time. And then a lot of the algorithms are like, you do the algorithm by basically like reasoning about the bit string that your processor is and moving like one at a time, like moving one bit at a time and flipping the bits as you go. So it kind of naturally comes from a lot of algorithms in some sense, but we will talk more about more complicated topologies because there are so many. Thank you. Yes.
This question on MPI. So MPI is basically an inter-process communication mechanism, right?
Mhm.
So where does it stand with respect to things like message passing or shared memory? Does message passing use MPI, or does MPI have other applications? Like how does it differ from other IPC methods?
I see. MPI is a message passing framework, and it can be used jointly with shared memory. Like it can be used with jointly with shared memory libraries like OpenMP.
So it's an alternative.
It is in shared memory. It is an alternative. In distributed memory, it is these days most like is these days the default way.
There's message there's the queue. Like you have the message queue.
Like in distributed memory.
Yeah, I think so.
Yes. Message passing is probably more common. And you can run MPI like we have been doing in shared memory. Right now we're doing the homeworks on one node. So it is also an abstraction that can be used over the course. But these days it is like when you have multiple nodes, it's like the default abstraction. And when you have one node, it is an abstraction, and you could also write, which we will not cover. But if you take my class next semester, we will, like OpenMP and specific shared memory libraries. So they're like, it's not based on this rank abstraction. It's more direct in threads.
And is there like can this be extended to machines, like processes not running on the same machine?
Yes. MPI, like, you can think of it as multiple different nodes. Like if you had multiple machines, each one of them would be one of the ranks. But you can also, like, you can also have multiple ranks per node, and that would be like the cores, I guess, or the threads. When you have them, when they're on multiple nodes, you need to do something like message passing or message queues. When they're in shared memory, you don't necessarily need to do message passing. You could just access shared memory. But in some ways, like from a programmability standpoint, like if you need to extend this, if you wrote, for example, like shared memory programs and you want to extend them to multiple nodes, you need to rewrite them in something like MPI. It's not going to work just to scale it into two nodes. But if you wrote an MPI program and then you want to run it on two nodes, it just directly follows. Does that make sense? Thank you. Yeah, so you can write like hybrid OpenMP and MPI as well. Yeah, so that is broadcast. And then with gather, again, every process has something, and then you're trying to put them on one rank. And yeah, so the function signature, you have a source buffer, source count, source type, receive buffer, receive count, receive type, root, and communicator. And the source buffer and the receive buffer should be different. So this is an example of how you would call it. You have a vector, which is the buffer. If your rank is 0, then you put you resize the buffer into the number of ranks that are in the entire world. You call gather. So source buffer is your own rank. Every processor puts their rank into rank. And then every processor is going to send their rank, one of them. There's one int. And then the receiver is going to get all the data into this buffer. And yeah. And then the root is 0. And if the root is 0, then we're going to print the entire buffer. And yeah, and at the end of this, just the elements will be in order in the ranks that they came in, so it'll just be the ranks in order.
So MPI gather is
Yes, the collectives are blocking. And another important thing to remember is that gather, this stuff is this stuff happens in order on the source, or it appears in order on the source process once you're finished, or on the root process, sorry. So the ranks would be printed in order here. The inverse of gather is scatter, and the function signature is pretty much the same. And so this is like a similar example as we had. But now everybody, or sorry, if you're rank 0, then you make this size buffer, and then you fill in, this is an example, you fill in the buffer of size number of ranks you have with 1 over 1 plus the rank. So this would be like 1 over 1, 1 over 2, 1 over 3, and so on like that. And then you scatter. Similar, but now you pass in the source, which is so this is the number of elements going to every process. This is not, notice that this is not size. So, and similarly in here, notice that the receive count is also not size. This is how many you're getting from every process in gather. And then in the inverse, this is how many you are getting to every process in scatter. And then reverse, this is how many you're getting from the root process in scatter. You're getting it into X, and every rank is going to get 1 over its own rank, 1 over its own rank plus 1. So like rank 1 would get 1 over 2, rank 2 would get 1 over 3, and so on like that.
It has to be different, the buffer or the sources information buffers have to be different in like scatter and gather as opposed to broadcast, where like the same one was used in both, right?
Yeah. The reason is maybe the sizes. Probably. Like here you're just getting 1 int, but like the source is a vector, but the destination is just an int here. Or like if it was generalized, the source would be a vector times p, and then like you don't need to scatter 1 int at a time. You can scatter a vector of vectors, but the source vector is going to be like that times p, and then the destination was just going to be that vector length. I guess that's why. Good question though. Yes.
Here they're the same,
What happens if they're different? Well, here they're also the same. You can receive less than you send, but you can never receive more. So like the send count could be, this could be greater than this, but it's never going to be the reverse. And then if you receive less, sorry, yes, you can, sorry, you can, no, sorry, I think I got to flip. Receive, you can always ask to receive more, and you may get less, but you cannot send more than your receive buffer can hold. That makes sense? So like, for example, if I say I'm going to receive 5 elements, and then there's a send for like 3, then the first 3 elements in my buffer are filled, and then the rest are garbage. But I cannot have a buffer of size 3 and receive 5 elements, for example. That makes sense? Thank you. Okay. So yeah, and there are also variants of gather and scatter with the V at the end, which is not everybody needs to get the equal length of stuff. So like previously for gather and scatter, everybody got equal length of data in that example 1 per. But for scatter V, rather than passing in 1 S count, you pass in a vector of them, which is, this is scatter. So this is a vector of length, number of ranks you have, and the elements just tell you how many elements you're going to send to each rank. They don't have to be all the same. In this example, oh yeah, and displacements. This displacements, which is the array of start indices. So you have a source vector that you're trying to scatter onto all the different processes, and S count is how many elements am I going to send per process, and displacements is where does that rank's element start in my vector. So the easiest way is if displacements is pretty much a prefix sum on source counts. Like for example, if I want to send like 2 to process 0 and then 2 to process 1, then displacements would be like 0 and 2. And I would just start where the previous process's stuff, all the previous process's stuff ends. So this is just some example code. You have a vector of send counts, you have a vector of displacements, and here we just have a 2D vector of characters. And we have four processes. And we make the vector into like a 1D, we make the matrix of characters into a 1D thing that's n times n. And then the remainder, which is if n changes from 4, then the remainder may become something that is not 0. And so basically we want to try, this is trying to distribute the characters as evenly as possible across the different processes. And the way you do this is like, you check if there's a remainder, and if there is, then you may need to unevenly distribute. Some processes may need to get one extra element. And then you determine that with send counts. So everybody initially gets the total number of elements divided by p into send count. Here. And then, yeah, if the remainder is not 0, then send counts may need to increment by 1, depending on if p evenly divides n, basically. And then you basically keep track of the sum and displacements. Like I said, this is the serialized prefix sum over the sizes. And so like you would just start everybody's elements where the previous person's elements ended. Yeah, you find the displacements, and then you do the prefix sum. Yeah, and then at the end, you just send whatever's in the send counts and displacements, and this can change. So for example, like if p changes to 3 rather than 4, or sorry, yeah, p can be 3, p can be anything, and then here it would be unevenly distributed, so the first one would need to get one more element, because if you remember, there are 16 characters, and 16 does not divide 3. Questions? The last couple of primitives I think that we're going to do today are all gather and all to all. So all gather is one process has some data that needs to go to every process, and then that data is going to be copied onto every process. Sorry. Yeah, that data is going to be copied. You're going to transpose this, and then you're going to copy it on each process. So, oh no, sorry. Each process has something, and then every other process is going to get all the stuff from the other processes. So like processor, got confused about the ordering. Processes is this way, data is this way. So process 0 has A0, process 1 has B0, process 2 has C0, process 3 has D0, and then in the end, process 0 has everything from all the ranks. In order, process 1 has all the same stuff, process 0, and so on. And again, it's ordered by the ranks. For all to all is like transpose, if you think of data and processes as a 2D matrix. Questions? So there are MPI function calls for all of them. For all gather, you take in, they all kind of look similar, like source buff, source count, receive buff, receive count, the 2 types. Yeah. And so for all gather, you have rank, and then you resize the buffer into size number of ranks that are here. And all gather is just, we put in rank in the source buff, put in 1. We put in the start of the receiving buffer here, and we put in 1. Again, this is not how many elements are there in total. This is how many for receiver. This is how many are we getting per process. And so at the end of this, what is in buff? It is everybody will get all the ranks in order, regardless of what you are. So like process 0 will get 0 through n. p minus 1, process 2. Process 1 will also get 0 through p minus 1, and so on. Yeah, okay. And finally, there's all to all, which is every process. Yeah, so every process has one message for all the other processes. This is like transpose. And again, the function signature is the same as all the other collectives. We have a send and receive buffer, which are now both equal to size, which is the number of ranks. And then we pass in send and receive. And then we're going to all gather one element at a time. And here we initialize the send buffer for I from 0 up to size. We set the rank into that thing. So the result is going to be the same as we did in the previous all-to-all. So the ranks, every process, before we call the all-to-all, every process has a vector with the ranks 0 up to p minus 1, initialized by this for loop in the send buffer, and then we put it in here. And then so every process is going to get 1 from this vector, and every process is going to receive 1 from this vector in the order that they appear in. So actually the result is exactly the same as the previous altogether, but in general, all-to-all and all-gather, you may not get the same results. And there are variants like all-gather, all-to-all v, which is similar to scatter v, like where instead of a single integer, you again get a vector of lengths, pretty much. Yeah. So to wrap up about the collectives, the way that you call them is that every process in the communicator has to call them. Like in the example that I was giving with broadcast, it's not like rank 0 is doing just the broadcast. And the way to think about it is that everybody's participating in the collective. They're all blocking. And you cannot assume synchronization. Like you cannot assume that the different processors proceed in the same lockstep unless you call MPI barrier. Yeah, they are guaranteed not to interfere with point-to-point sending. And they are implemented with point-to-point, as you will see. And these are just the things that we went through: scatter, broadcast, scattered, gather, all-to-all. Questions on this part? I think I don't have that much left. I have a tiny bit. Yeah, so previously we did the collective communications, which are just sending, like there's no computation involved. There are basics in MPI, like reduce and scan, that we will just do in a moment, that involve like a tiny amount of communication, but they're still called collectives. So yeah, so there's reduction, which is just you want to add up everything into one single element. And we talked about how to do these in parallel in algorithms, and there's just MPI functionality to do this. And it's similar to the collectives. You have a source buffer, you have a receive buffer, you have a count, and you pass in a type, you pass in an operation, and then you pass in a root. So everybody, assuming that every processor gets their element, the source buffer is A, which is some data. The receive buffer is sum, which is again the same size as A. You are adding one thing, which is the count, 1, int sum, and then the root is 0. So the answer is going to show up on rank 0. Yeah, and notice that count does not have to be 1. And if you don't pass in count as 1, then both receive buffer and source buffer should be vectors, and you do like vector-wise reduce. So like in the end, the 0th element on the source, or the 0th element on the destination root would be the sum of all the 0th elements and all the vectors in the ranks. And then similar for 1, like it's just like lane-wise addition in this example. And MPI supports, like, it already provides these things like MPI sum, stuff like that. Under the hood, those are just like integers, and then at compile time, it passes in. At compile time, it determines in what operation it is. I think up to some limits. Yes, I think you can compose some of the operators. Good. So yeah, they have MPI sum and they have a bunch of other ones: min, max, product, logical AND and logical OR, bitwise AND and bitwise OR. And you can compose different operations, I think. Oh yeah, and you can only do it in parallel if the operator is associative. So reduction, all reduce, which is another primitive, is just an MPI reduce plus an MPI broadcast. So everybody has some stuff. This is the signature. You have a send buffer, you have a receive buffer, and you have a count. So all reduce is you have some data on every process. You gather it, you reduce it onto one process, and then you send the result onto everyone else. And this is just an example, like if this is the termination condition 1 or 0, and you all reduce the termination condition, and then you check if anybody has terminated, then you finish. Yeah, this is an example of reduction. This is initialization. You would never actually really do this for reduction because then this is just an example because like this is basically you scatter all the data onto different processes and then you reduce them back. But you would never actually do this in practice because you already have all the numbers on your single process and you have to pay the communication cost, which is higher than the cost that it would do the addition anyway. But this is just for illustration. So you scatter all the data onto the different processes, you reduce them back into value, and you check, is it this correctness validation? You added them all up. So you did the work anyway on one process here, but you're just validating that you got the correct answer. But in reality, you may get slightly different answers because floating point math is not associative. But that's just an illustration for how to use reduce. In addition to reduce, they also provide functionality for prefix sum. They call it scan. So again, the function signature is exactly the same. Send buff, receive buff, and count data type operator. And we talked a lot about parallel prefix, so I'm not going to go over it again. This is doing a parallel prefix over the ranks.
What would be the difference between
Reduce gets you one element, and scan gets you, or sorry, reduce is one element onto the root, and scan gets you one element on every process. So like prefix sum, you get a vector A, and you get it out a vector A prime, where every element is like all the sum of elements up to I for every position I. So you can think of just MPI scan as every process has one of the elements in the prefix sum. And so what is going to happen at the end is that in order of ranks, rank I is going to get the sum of elements from ranks 0 up to I. Does that make sense? So there's no root in scan, but reduce has a root because everybody's numbers are going to get added up onto the root. But here, everybody is going to keep the same size of data that they had, but just the result is going to be like if you did a prefix over the entire, over all the ranks. Mhm.
array, and then like as process, like they will have like larger.
Yeah, so like suppose that count was just 1, processor 0 would have its original element, processor 1 would have its element plus the element from processor 0, processor 2 would have the elements 0, 1, and 2 added up, like that. And you can pass in count because similar to reduce, like you can do this kind of like along the lanes of the vector. Reduce in scan, you can also do like along the lanes of the vector. Good question. Does that make sense? Where the elements are distributed across the different ranks.
Send what
Count?
Yeah.
Count is just the number of elements per rank. So, for example, like if every rank had one element, count would be one. Oh, count is for if you want to, like if it's one, it's pretty obvious what it is, but if it's multiple, it's, sorry, start picture. So let's say that count is 3. So then this is like P0, this is like P1. Let's just do 2, for example. So if count equals 3, then this would be like this. So if this is like A0, B0, or no, sorry, A2, A1, B1, B2, the result would be like on P0, you would get, yeah, that's right, I think so. Get A0, oh yeah, those are all the same. They stay. And then P1 is A0 plus B0, A1 plus B1, A2 plus B2. So you are doing it this way. Does that make sense?
Also, is like the resulting prefix summary like in place? So are you overriding the original path?
You pass in different ones, like send buff and receive buff are different. Like this is, like rank is the input to the prefix sum, and prefix is the declared output. I don't think so. Let me check that. Because would you just take the min then? How would you, like for example, if you have a vector.
Some you're doing the n over p process, hopefully, and then do the full. I don't know if it's doing this over p internally, and then.
Oh, I see. But then when you do n over p, oh, you cannot pass in like your n over p vector into the collective because it's doing like this lane-wise thing.
Oh, it's doing
Yeah. Like, I guess it's a bit hard to see with two processes, but like, if you had, let's say, a vector of length 3 on each process, P0, P1, P0, the results are the same. After the scan, the results on P0 are as they are because you're doing prefix sum over the ranks. So like, it's not horizontally, it's like vertically in this way. So P1 would get a vector of length 3 where every element is like the sum of both of the things in the same slot from P0 and P1. And then so on if you increase the number of processes. I don't think so, but let me check. Because the lanes kind of need to line up. I'm not sure what it means if like some call it on fewer lanes.
Okay, so each processor will essentially have an entire layer. It's not like we're splitting the
No, each processor will have, in this example, each processor has one element, and it will end up again with one element. You can think of like in the prefix sum, you have a vector, and here each element of the vector is on one rank, or each element of the vector is on a different rank. And then in the end, each result will also be on a different rank, which is the corresponding result from the prefix sum.
So like if we actually have
Like if you had n over p elements on your process, you could locally reduce those with like addition or whatever, and then you could pass that into scan. Like you could implement the prefix sum algorithms that we have been discussing in class using MPI scan. But if you remember, like one of the steps in that is to do the local reduction first, and then you do like the end thing.
only ever takes it.
You can take in more than one, but it's not going to, it doesn't reduce horizontally across the vector that you pass in. It reduces vertically across the ranks. Yeah, so that is how you do parallel prefix. And then I have like 3 minutes. I don't think you actually need to use this in the homework, but just really quickly, you can, like I said, create custom communicators. Like in the beginning of time, you get ComWorld, which is all the ranks. If you want to get a subset of the ranks, you could call com split, which is, so yeah, there's com dupe, which is just duplicating the same communicator, and there's com split, which is you split your initial communicator into based on this color. So color is just an int, which is identifying like what group it's going to be in, basically. And then key is the initial, is the ordering that you want to give it in the new communicator. So like key could be its initial rank, and then you get out a new communicator. And so this is also a collective in the sense that everybody in the communicator is going to call com split, but not everybody is going to get the same new com out based on the color. And I'll show you an example in a second. Oh, yeah, and then you can release the communicator. Yeah, you get a new communicator based on the color, and all processes with the same color belong in the same new communicator, ordered by the key that you pass in. And the main use case for this is like if you want to implement divide and conquer, you may want to split the processes like half and half, for example, and recursively like half and half. Yeah, so just an example, the color is just whether you're even or odd, so it's rank mod 2. And then you call com split, which is the initial com world, the color, which is whether you're even or odd, the initial rank, and the output communicator, which is this thing. And this, what is going to end up here, you're going to get two communicators out of this, one with all the even processors and one with all the odd processors. And they're going to be ordered by order of their rank, starting from 0. So in the even ones, you would have like 0, 2, 4, 8, 0, 2, 4, 6. But those get mapped into 0, 1, 2, 3. And same for the odd ones, you have like 1, 3, 5. But those, again, get mapped into 0 indexed processes. So like 1, 3, 5 would become the new 0, 1, 2 in the odd communicator. Yeah, and then this reduction is the only difference from the plain reduction is that now you call on the new communicator. So now you're doing two independent reductions, one across the odd ranks and one across the even ranks. Yeah. And then rank is just what it was initially. And the result is, yeah, so the two communicators are now even, 0, 2, 4, 6, 1, 3, 5, 7. And the color is just even or odd. And then the key is its initial rank. But the new ranks that they get in the new communicators, like I said, the ranks cannot overlap in the different communicators, like 0, 1, 2, 3, 0, 1, 2, 3. Yeah, and then the final result, we've reduced across the ranks. And then on 0, so there's two communicators, even and odd. On 0, you get 12. On 1, you get 16, which is the result of adding up the initial ranks, the even ranks onto 0, the odd ranks onto 1. Yeah, there's just a couple of defaults like null and self, which is just empty and yourself. This is for like if you want to avoid some ranks participating. You should keep a reference to you will keep a reference to the initial one. Like you pass in this com world, but you have to, the output is in a new communicator here. So you always keep around the initial ones. So this com is declared on every rank. And this com, after you call com split, is different depending on if you're even or odd. So initially in the beginning of time, there's only com world. And then now you're passing in com, which is based on the color. Does that make sense? Thank you. Yeah, I think we are out of time, but yeah, thanks.